Okay, so welcome back to our channel, and in this video, I'm going to redo this example 2 in one-way ANOVA, but this time I'm gonna use a new software called JASP. So let me read this. A researcher wishes to try 3 different techniques to lower the blood pressure of individuals diagnosed with high blood pressure. The participants are randomly assigned to 3 groups, and the first group takes on medication to lower their blood pressure. The second group exercises, and the third group follows a special diet. And after 4 weeks, the reduction in each person's blood pressure is recorded, and at alpha 0.05, test the claim that there's no significant difference among the means. So we can see the values here. We have 15 persons, for 15 participants, and they're grouped according to 3 groups. And we can see that participant 1 are under the medication technique, and it gave him a reduction of 10 in his or her BP. Participant number 6 got a reduction of 6 in his or her BP, and participant number 15, that is after participant 6 after doing exercise, and participant 15 after doing a special diet, had reduced 4 in his or her BP. Now, of course, we would want to write first the hypothesis of this study. And for the hypothesis, we would like to first determine the dependent and the independent variables. We know that the blood pressure is the dependent variable. Remember that it's required for you to have a continuous and interval or ratio dependent variable for one-way ANOVA. There's also the same with independent samples t-test. And the independent variable are the techniques to lower blood pressure. So remember that there are 3 categories or groups in the independent variable, so we need to use one-way ANOVA. If there are only 2, we just need to use independent samples t-test. And for the hypothesis, this is how we state the hypotheses of a study. And for the null hypothesis, we're saying that it's the status quo, so there's no significant difference among the different techniques. I mean, their blood pressures of the participants were have equal or almost similar, not equal, but similar reduction in their BP. And for the alternative hypothesis, we are claiming that there is at least one technique which is more effective than the others. So in order for us to set this up, we're not gonna write this in JASP as in the way this is written here. Instead, we're gonna make sure that the dependent variable is found in one column and the independent variable should be found in one column. So after a bit of data cleaning, we will end up with this kind of setup. So notice that the BP reduction are all in one column and the techniques are also in one column. If you want, you can copy this setup in JASP. By the way, this is JASP, everybody. This is the icon for JASP. You can download JASP. It's free, similar to Jamovi, the one here. And try it yourself. And if you want to copy, please pause the video and copy this information so that you can get along while during the analysis. So let's start. First up, obviously we're gonna click on this icon entitled ANOVA, and under ANOVA we have several options, and we have 2 main categories here: classical ANOVA and Bayesian ANOVA. Classical ANOVA are also known as the frequentist approach. Bayesian approach is another approach, but in this video we're gonna start and we're gonna do the classical approach. ANOVA is the classical one, which is the extension of independent samples t-test. Just to explain some parts here, repeated measures ANOVA is the extension of the paired t-test or the dependent samples t-test. ANCOVA is the analysis of covariances, and MANOVA is multivariate analysis of variances. So we're just gonna concerned as far as this video is under here in ANOVA. So I'm gonna click that, and JASP will bring me to a setup wherein we can see now in the screen that there are 2 sides. On the left side, we can see the input part, and the right side we see the output part. In the input part, we do the setup that we want. And it's just JASP telling us what do you want me to do. And after doing the setup on the left side of the screen, JASP will show the results on the right side. So first things first, we need to set up our variables, and we know that the BP reduction is the dependent variable. It is also obvious that in the dependent variable box on here, there's a ruler icon and indicating that it should be continuous. So I want to drag this one going here. There are two options. You can drag and drop, or you can just highlight that variable and then click this arrow head here going to the right, and then there you go. And of course we need to fix some fixed factors or our independent variables. I'm just gonna drag it going here and it will be there. Notice that the dependent variable is only one. We can only input one dependent variable, and in the fixed factors we can input more than one. That will mean that if there's one factor, it's going to be one-way ANOVA or one factor ANOVA. If there are two factors, that's going to be two-way ANOVA, and n-way ANOVA will be different factors. But the more factors you input, the more far-fetched it will be. So that's why you just commonly hear one-way ANOVA or two-way ANOVA. You can do three-way and four-way, but it's not commonly used. Okay, so on the right side of JASP, we can see already the initial results. But remember that before we believe these results, we need to double check for assumptions or some violations. Maybe there's some violations in ANOVA. Remember that in one-way ANOVA, we have two major assumptions. Number one is normality. So the distribution should be normal. And number two is that homogeneity of variances. So to get everything, in a single analysis, I'm just gonna click things that will be so that will be a single take. I'm gonna check on descriptive statistics. I wanna check on this estimates on effect size, and I don't. I usually use eta squared for one-way ANOVA. So I'm gonna uncheck the omega squared, just the eta squared. I'm gonna click on the assumption checks, and I want to check on the homogeneity tests. I'm gonna check on the Welsh under the homogeneity corrections. I'm also gonna check on the QQ plot for residuals. So after that, I'm also gonna click on the drop down of descriptive plots, and I want to drag these techniques to the horizontal axis here, and I want to check on the error bars, and I'll just let it be. And I'm also gonna check on the non-parametric statistics and drag the techniques going here. The non-parametric counterpart of one-way ANOVA, by the way, is the Kruskal-Wallis test. I'm just gonna drag it there, and okay, let's see the results. Okay, so on the first table, you can see already the results of ANOVA, and there are two results here. Mainly the student's t-test, wherein there are no homogeneity correction, and the Welsh test. We use the Welsh test if there's a violation in the assumption of homogeneity of variances in the population. So we're gonna skip that for a while. And then I guess we could actually just first observe the descriptives part of the data so that we can see an overview. Okay, here we go. Here's the descriptive plots that I've been waiting. So that we can get a glimpse of what is happening with the data, descriptively speaking. And we can see very clearly in the descriptive plots, we have diet, exercise, and medicine. By the way, I have used some acronyms. EXE means exercise, med means diet. Med means medication. Apologies. And diet means, of course, diet. And we can see that medication is the one which has the highest mean, meaning it offers the one with the highest reduction in blood pressure. This is followed up by diet. You can see the means there, which is denoted by the black dot, and the error bars displaying the confidence interval. And the exercise has the lowest mean. This can also be verified in the descriptive tables. You can see diet has a mean of 7.6, exercise has 3.8, and medicine, when you take up medicine, the BP reduction is 11.8 in average. We can visually see that medicine offers the highest mean value as far as reduction in BP is concerned, followed by diet and exercise. So we can say that the medicine has a higher mean, but we cannot say yet that it's the most effective. Remember that the data is taken from a sample, and also remember that samples, if it is random, is there's a possibility of chance. These are only, we took this data only from 5 individuals. So in remember, in inferential statistics, what we want to do is to go and give the conclusion back to the population. So we use inferential statistics to make sure that there are no chance factors involved. So that's where the p-value comes in, to let us know that the results did not happen by chance. Okay, so since that's what we want, we have a hunch that medication gives us the most effective um, technique to lower the blood pressure. So before going to ANOVA, we want to go down first to the assumption checks. And we have two assumption checks, remember? Normality. So the normality can be seen in the QQ plot. Very visual and simple test. Can you see? I hope you're seeing the red diagonal here. If most of the dots are near or on the red diagonal, there's no violation in the assumption of normality. So visually speaking, we can see that most of the dots are on the diagonal. So therefore, there's no violation. Hence, we can say that the data is normal. So okay, no problem regarding that. Next is, so normality is not, by the way, normality is not violated. The moment that normality is violated, we will be shifting to the Kruskal-Wallis test. That is the non-parametric counterpart. If normality is violated, we go to the non-parametric counterpart. Okay, so since normality is not violated, we'll go ahead to the next assumption, which is the equality of variances or homogeneity of variances. So one important assumption is that the variances of the population should be equal. Okay, or the variances of the populations. So one thing to check that is using the Levene's test of homogeneity. So we can see that the p-value is 0.689, indicating that there's no violation in the assumption of variances. Why is that? Because the null hypothesis is the variances are equal in the population. So if it is rejected, meaning we go that there is a violation. So since the null hypothesis is not rejected, and that's what we want, so there's no violation in equality of variances. So since there's no violation in normality and there's no violation in the homogeneity of variances, we will be using the student's t-test. Sorry, the Fisher's f-test rather. Okay, I guess I have mentioned earlier that students, no, it's Fisher's ANOVA. We use the Welsh ANOVA if there's a violation in Levene's, and we use the Fisher's ANOVA if there's no violation. Actually, we use the Fisher's ANOVA if there are no violations at all, both in normality and homogeneity. So we're gonna follow this. Remember that parametric tests are the one which has the strongest and robust results, and of course the standard in research literature. So we're gonna follow this one. So notice that in the first row in this table here, the p-value is 0.004, okay, indicating that there is a significant difference in the different techniques in lowering the BP. Okay, so meaning at least one of them is effective. Now, a word of caution: if the ANOVA results is significant, it is incorrect for you to just look at the means and just conclude that medicine is the most effective and that and exercise is the least effective. We call that eyeballing the data. Eyeballing again. We call that eyeballing the data, and that's illegal in statistics. What we want to do is to double check using a post-hoc test. So I'm gonna click on this. I'm gonna show the inputs. Post-hoc is Latin, which literally translates to English as in after that or after it. I'm gonna click on post-hoc, and I'm gonna drag the techniques going to the right side box. And since it is we're using the standard and Fisher's ANOVA, we're just gonna click the standard and let the 2 key correction there. If ever we will be using the Welsh, we're gonna check on the Games-Howell, and if ever we're gonna use Kruskal-Wallis, there is a a post-hoc test here, which is non-parametric, which is Dunn's. All right. So again, you can just review the video. I'm gonna click on stand type, We're gonna click on Tukey. We're gonna click on flag significant comparisons, and I guess that will be it. That's enough for that one. Okay, you can add more statistics if you need, but we're gonna scroll down here, and we can see under the post-hoc tests using Tukey that the purpose of this asterisk is for to make our lives easier. And if ever there are asterisks in the p-value under Tukey, it tells us that it is significant. Okay, so meaning when we compare exercise and medication, it is significant. Notice that the T score gives us a negative value, indicating that the right category is one which is more effective. So when we compare exercise versus diet, exercise versus medicine or taking medicine, taking medicine is more effective than exercising if you want to lower your blood pressure as far as the data is concerned. Meaning, notice that the categories, when you compare it with diet, the p-value is not significant. So meaning, when you compare diet and exercise, it doesn't really have a significant difference. So meaning you can either choose one of them. If you're gonna choose between diet and medication, you can either choose one of them. But when you're given a chance to choose between medication and exercise, you should always choose medication because it gives you a more effective reduction in BP. Now, before I end with this video, I want to teach you how to properly report them in your writing. So, if I may, I will be adding a note. Where will I add a note? Maybe here. I'm gonna separate in the analysis. I'm gonna add a note here. I guess that's wrong. No, I want to add a node under this table, not above that. Okay, so how do we use or how do we report the analysis? So I'm gonna do the reporting separately, one for the one-way ANOVA and one for the post-hoc test. So be with me. Regarding the English parts, you can always use different words. Okay, but what should be strictly followed is the way the statistics is reported. So again, for the English, using one-way ANOVA, you can before we start, you can actually discuss first the assumptions check. So using the QQ plot, using the Levene's test, but I'm gonna skip that one. You can always bring that up in the results and discussion. No problem regarding that. But I will start with this one. So using one-way ANOVA, F-test results reveals that there is a significant difference in the BP reduction. I'm gonna spell it out. Blood pressure reduction when, or shall we say, in terms of, what do we call this? The technique used. Okay, and then this is how we report the statistics. Seldom statisticians don't use this, but I personally use this. It's up to you if you use it. I start with open and close brackets just to differentiate it with the parentheses, but some statisticians don't use it. It's up to you, but this is the important part. Since we're using F-test, I'm gonna start with clicking on the F-tests. Let me make this larger so that it will be emphasized. Open parentheses. We're gonna enter the 2 degrees of freedom, yeah, and we're gonna type 2, 12. Okay, then close parentheses. So meaning after the F, we're gonna input the degrees of freedom that we have, and then we're gonna click on equal sign. The equals will be the F value, so that's 9.168. I'm gonna input then the P value, which is equal to 0.004. Usually in p-values, we omit the leading zeros. So I'm just going to input 0.004. And then comma, lastly, this is, for some, this is not yet common, but we want to make it now commonly used. We're going to input the eta squared or the effect size, all right? So there's no shortcut for effect size. I'm going to type it in LaTeX. So I'm just going to type eta squared. I'm going to click enter. And eta squared is equal to 0.604, and I'm just gonna make that a bigger font. Okay, there. Now, regarding effect sizes, remember that the p-value only gives you that much. The p-value only tells you if it's either due to chance or not due to chance. So it doesn't really give you how much effective it was or the practical significance of the test, and neither you cannot use the p-values for to compare it with other studies. But the effect size could be used to compare with other studies. So the p-value indicates that it's not due to chance. I mean, there's really a difference, but effect size gives us the magnitude of the difference. So going to Google, you can see this effect size from Cohen, from his book Power Primer. And the effect size here that we use is the eta squared. This is the partial eta squared, but nonetheless, it uses the same interpretation with the eta squared. Small effect size is when your eta squared is 0.01, medium is 0.06, and large if it's 0.14. Okay, take a look at that. And our effect size is 0.6, so that's very large. So we're gonna input this in the results reveal. Results show that this is a large effect. We can then cite Cohen here. When was that published? Cohen 1992. So let's follow that. 1992. All right. There you go. Okay. Now that's how you write. You do the write up in ANOVA. Let's finish this up. So you can just pause the video if you want, but I'm gonna finish the write up in the post-hoc test. I'm gonna add a note here. And what's happening? Okay. That's wrong. I'm gonna add a note under the table so that you won't get confused. So again, the English parts you can edit them since one-way ANOVA shows a significant result. We will use a post-hoc test to determine where the significant difference lies. Right. Using 2-key. Actually, the name of 2-key is HSD test. Honestly, significant difference test. So HSD test results show that there is a significant difference when we compare medication. We compare the medication technique. Then after that, you can actually, this is optional. You can add the mean and the SD of that technique. The medication's mean is 11.8. The SD is 2.38. Okay, let's do that. 11.8. What was that? 11.8 and then 2.387. 11.8. SD is 2.387. Okay. And the exercise technique, we're gonna copy the mean. Mean is 3.8 and 3.8 for the mean. Let's do that step at a time. One step at a time. 3.800, and the SD is equal to 3.194. 3.194. Okay. How did I get these write-ups? By the way, you can just go to the APA formatting. This is the 7th edition APA that I'm using, so you can verify that over there. And of course, we're gonna input the p-value. P-value equals, again, we omit deleting 0.003. Okay, and then after that, we can actually say, since there are no other significant difference occurred, no other significant difference observed. Okay, and that's it for this video. You can pause it so that you'll have a copy, but hopefully you learned something here, and that's how you analyze the things in using one-way ANOVA. It's quite different from my previous videos. Of course, we improve as we go along in this field, yeah, this is the latest video, the latest update. So the thing that I want to significantly add is the effect size, because it gives us the magnitude of the difference. And of course, Cohen, it gives us an interpretation of this. So this is a large effect. And of course, the way statistics are reported in paragraph form is very much important. Giving numbers without the interpretation is doesn't make sense. So you should be able to make sense of the numbers presented here. Okay, so thank you very much. Hit me up in the comments if you have some questions, and don't forget to hit like and subscribe. Thank you very much.